Our term project is Practical Early Parsing by Sam Kuhl, Kenneth Grovenberg, Austin Posey, and Michael Bailey. An early parser is an algorithm that is used to parse context-free grammars. It has the main advantage that it can parse all context-free grammars, and it doesn't have to be converted to another form, such as Greibach normal form or Chomsky normal form. Given a context-free grammar G, it can determine if a given string W is a member of the language generated by G.
An early parser works by creating sets of early productions which represent how much of the string has been processed. It uses the operations predict, scan, and complete to populate the sets. The predict function adds the productions of a non-terminal variable to the current set. The scan function parses a terminal variable, and if it matches the string position, it is added to the next set. The complete function finds possible origin points of productions, then parses and adds them to the current set. Using these tools, it can parse through the string and determine if the string is valid or not.
The addition of the new lambda rule. Early parsers can get caught trying to process nullable variables, since the complete function will try to pull its possible origin from a non-complete set. This can lead to some strings being denied when they should be accepted. A new rule is added to the predict operation, which stipulates that if a nullable variable is being predicted, it should parse past that and add that production to the current set, as well as predict it normally.
For example, given our following grammar, S produces A produces little a produces E, and E produces epsilon. As demonstrated by the parsing tree on the right, the string just small a should be valid. The early processor says that this string is invalid, as it can be shown from not having enough productions to properly parse. But once we add the lambda rule, the early parser says our string is now valid and can be shown as additional productions generated can lead us to parse correctly for a full production. And here we demonstrate a bit of our code. As we can see here, we demonstrate the generation of the grammar through its production rules, its list of non-terminal variables, and terminal characters, constructed into a grammar G, and sent to the early processor with our desired string and our flag to turn on our lambda rule. Shown here is a little bit of code to help determine whether or not our term is nullable or not, so we can use it to later figure out if a production should get the lambda rule applied to it or not. Now, as we can see here, we show off our three early functions. Our first function, complete, if we come across a production that has finished parsing, we go to the original set it's in, and we find if it's a possible origin point. Then we parse past it, and we push it onto our current set. Our scan function, if we come across a terminal character, and it matches where we are expected to be in the string, then we parse past that, and we add it to the next set. Then finally, our predict function, where if we come across a non-terminal variable, and our lambda rule isn't active, we distribute all the productions it has with that rule and sends it to our current list. However, if our lambda rule is active, we predict as normal, but we parse past the non-terminal and we push that onto our current set as is. And if it's non-nullable, then it just predicts as normal.